Hi, Dylan. Whoa. Hi, Dylan.
Hi, Professor Popovich. How are you doing today?
I'm doing fine. You did okay on the calorimetry. You did okay on the calorimetry results. So it seems like you're understanding what's going on here with that stuff anyway.
I think so. I hope so, at least.
You have any questions about anything? I mean, I've got 10 minutes here.
I had one question about the pre-labs and post-labs for, I think it was density of liquids and solids. Are you going to open that before the exam?
Well, I'm sorry, I'm not understanding. Am I going to open it? You can't see it now? Dylan, you can't see it now?
No, not my answers.
Okay, let's see. I'm gonna stop share. I got a few minutes anyway. Okay, we're in here. Yeah, okay. Stop it. Okay, so the pre-labs for
post-lab specifically for the densities of solids and liquids.
I'm not even saying it, for God's sakes. Ionic compound, titration, standardization. Hi, Jasmina. Oh, here we go. Dylan, you're saying it as I'm saying it, okay?
Okay.
All right, I'm showing. It didn't even have a start date. The only thing it had was an end date, okay? And, oh crap, stop that. Hi, Jasmina. Okay.
Hello, how are you?
I'm doing fine. Basically, thank you very much, Jasmina. You were absolutely correct. I don't know what I was thinking when I did that, but the right answer was neon. And you got a
No
point.
worries. No worries.
You got a point for the quizzes. Okay. I mean, you're seeing it, Dylan.
Yeah, I see it now. I don't know why it wasn't pulling
I
up
don't
earlier.
know why that's not popping up for you. I don't know what to tell you. Dylan, nope, that's not what I wanted to. That's what I wanted to. Okay, so I'm gonna go in here. And it's probably not going to do me any good because I don't think I answered the question.
You know what? I lied.
Okay, thank you. Thank God you lied. Hi,
It was
Angie.
post-lab for standardization of a sodium hydroxide.
Okay, I got to get out of here. Did I sign out? I did not sign out, did I? Yeah, I did. Son of a gun. Okay, close your eyes. Hi, Angie. Hi, Vanessa. Okay, now I got to go do this. All right, sorry, guys. Anybody have any questions other than Dylan? I'm trying to fix something for him. Anybody have any questions in general? You guys did okay for the calorimetry lab for the most part. Okay, here we go. Quizzes, Dylan. Angie. Are you there yet, Angie?
I'm here.
Okay, I need to talk to you about the last lab, okay?
About the what?
About the calorimetry lab.
Oh, I messed that up really badly because I didn't watch the video before doing it, and
Okay.
I totally messed it up.
Okay, so I that makes me feel good because the results weren't typical of what you give me.
I'm sorry
Dylan,
about that. That was totally my negligence.
Dylan, what was the lab? Post lab
And
for standardization of the base?
sodium hydroxide, yeah.
Find this silly thing. Where? Formula, sodium hydroxide. There we go. All right, edit. Okay, restrictions. Sorry, guys, I'll be right there in a second. All right, you see, Dylan, no start date, no due date, just the end date, right?
Yeah.
This may be the other problem. I'm hoping it is, because if it is, our problem will be solved. If not, then I don't know what to tell you. Yeah, nope. There we go. That you want your answers in the other thing, right?
Yes, please.
Done.
Thank you.
Check it in the next day or so and see if it's right. Okay.
Okay, thank you.
Anybody have any other questions? Those of you in the lecture, quiz 6 or quiz 14, question 6, the answer was wrong. It should have been neon. I corrected it for those that got it, that had it marked wrong, and I also marked it wrong for those who marked the incorrect. They got credit for fluorine, which was, for some reason or other, I don't know why, that I marked that as the right answer. Sorry about that. Anybody have any questions about the lab? Okay. Couple things about this lab, okay? And I'm going to stop sharing right now. Couple things about this lab. You have to do a graph. You have to do a graph. And literally speaking, ladies and gentlemen, the best way for you to do that graph is through Excel. Are you all, is anybody familiar with how to do an Excel graph?
Yeah.
If you could do an Excel graph, believe me, that is a skill that you're going to use over and over again. So if you notice, can you see the screen I have up here?
Yep.
Okay. If you see the screen I have up here, down, third thing down, I have a video that shows you how to plot a graph in Excel and how to find the slope of the line of best fit. And that's really what we're going to need tonight, okay? Believe it or not, guys, expend the 15 minutes. It will save you hours and hours graphing. Okay, so that's there. I've also, at the very bottom of this, included the Beers Law PowerPoint presentation, which is the one I'm going to go through, okay? So you have those two things. I will post the video sometime tonight. Are we good about that? Okay. The equations aren't that difficult. It's not that difficult, but the thing about it is something, it's something that you're not going to get in lecture. The only time you're going to see this is in the lab. So it is kind of crucial that you guys are here tonight. Okay. The equation, overall equation we're going to be using is this one, where the absorbance, the amount of light that gets absorbed by a substance is going to be equal to something called this funny looking E, which is actually an epsilon, which stands for the molar absorptivity, B, the cell length, and C, the concentration. So if we have something that's going to absorb light, and we know the concentration, we know how far the path length of light that goes through that substance is, and we know the molar absorptivity, we can calculate what its absorption should be. Now, look at the two shirts. Different dyes make up these shirts. Do they absorb light to the same degree?
No, sir.
So the absorption of light has to be dependent on the compound that is placed in the path of that light. Does that make sense to you? You see, this
Yes,
is where I
sir.
pause. This is where I pause and somebody yells, yes. Khalil, you're going to be my yes man tonight?
Looks that way, sir.
All right, good enough. Okay, so the amount of light that gets absorbed is dependent upon the compound that's in the path of the light. Now, if I have two different cells, okay, and if I concentrate, if my concentration is doubled, so the path length of my two cells, this one and this one, the path length is doubled over, I'm sorry, excuse me, the concentration is doubled over here as opposed to this. The path length is the same, but the amount of stuff it sees is doubled. Can you see that if the light is seeing many more atoms of the compound in the concentrated cell, can you see that that is going to absorb more light?
Yeah.
Yes, sir.
Okay. The last thing, if I keep the concentration the same, but I double the path length, again, is that light not going to encounter more atoms of the compound that's absorbing it? You're on, Khalil.
Yeah. Yes, it will.
All right. So absorption of the light depends upon the compound that's absorbing that light through, and we measure that through a constant called the molar absorptivity. It's also dependent upon the path length, and it's also dependent upon the concentration. We can control one of those things. We can control the path length. If we make the path length 1 centimeter, then in my expression, absorption is equal to EBC. My B goes away because it's one centimeter. Now, Khalil, if you've got nothing in there, if your concentration is 0, what do you expect the absorbance to be?
The absorbance will be 0.
Okay, we got 0, 0. Okay, at the point 0, 0, Khalil, what is the y-intercept?
The y-intercept is
Come on, you can say it. If we're at 0, 0, at what point on the y-axis does the line cross the y-axis?
I could with graphs. Crosses at
At
0,
0.
0, right?
Yeah, 0. It crosses the y-axis at 0. So the y-intercept is 0. So,
Yeah.
Dylan, if I have an expression now where my absorbance is equal to molar absorptivity times the concentration plus this 0 here, what does that look like the equation of? Think back to algebra. Could it be something like y is equal to mx plus b?
Yes.
It looks very much like that. So, ladies and gentlemen, if I plot as my y the absorbance, and if I plot the concentration as my x-axis, because of this equation, I'm going to get a straight line. And if I get a straight line and I take the slope of that straight line, I am going to get my molar absorptivity. Is that kind of understood? But is anybody confused by what I just said?
I'm good.
Okay. So what I'm going to do is I am going to plot my absorbance on my y-axis, my concentration on my x-axis. I am going to get a straight line, and that straight line is going to have a slope value and a y-intercept value. The slope value is going to be what the molar absorptivity is. Does this make sense to you guys?
Yeah.
All right. Now,
Yes, sir.
one more thing before I forget it. Excel programs do not like scientific notation. I'm sure there is a great way that you can enter it into those little boxes and print out something like this. I haven't found it yet. So unfortunately, what you're going to have to do is, when you see this is 1 times e to the minus 4, when you enter it into the Excel box, you're literally going to have to enter that in as 0.0000100. Do you understand? Because if you don't, what's going to happen is this is going to be a concentration of 1, 2, 3, 4, and 5, and that's going to throw your slope way off. Does that make sense, guys?
Yes,
Yeah.
sir.
All right. So the whole purpose for the first half of this experiment, the whole purpose is to obtain this graph. That's it. So we're going to create a series of solutions with different concentrations. Then we're going to put each one of these solutions into a UV spectrophotometer. And we're going to measure the absorbance of each one of these different concentrated solutions. We're going to plot the absorbance versus the concentration. We are going to get a straight line. The slope of that straight line will be the molar absorptivity. Okay, so we've got half of the lab done. We've done the graph. We've gotten the straight line. We have the slope. Now, what we're going to do is we're going to dilute our Gatorade down to a certain level. And then we're going to put our Gatorade diluted mixture into the same instrument. And it's going to register an absorbance. At this point, all I have to do is take that absorbance, which is going to be a number between 0 and 1. I'm going to take that absorbance and I'm going to divide it by the molar absorptivity, which you just found out was the slope of the line. So you're going to take the absorbance, divide that by the slope of the line. That is going to give me the concentration of our diluted sample. Okay. Then once we get the concentration of the diluted sample, we're going to reconfigure it back to what it was when it was concentrated. That's the strategy we're going to do. So first part, we're just doing our dilutions. We're just doing our dilutions to get the graph. To use the formula we're going to use to get the concentrations is M1 V1 equals M2 V2. For our first solution, these are our 4 solutions that we are using. We're using these solutions to get absorbances to do the graph. Our first solution, our stock solution, has a concentration of 4.75 e to the minus 5th molar. I need to take 1 milliliter of that solution. And what I'm going to do is I'm going to pipe that up 1 milliliter. Very accurate. 1.00 milliliters is what 1 milliliter is. I'm going to take that. I'm going to transfer that into something called a volumetric flask. A volumetric flask will measure one volume very, very specifically. So I'm going to take 1.00 milliliters of my stock solution, put it into this flask that is 250.0 milliliters. I'm going to then add the deionized water until I just get to the line. So what I put in there was 4.75 e to the minus 5th molar. I multiply that by 1.00 milliliters. This is my M1 and V1. My M2, I don't know. My V2 is 250.0 milliliters. I do that math out, I get a concentration of 1.90 e to the minus 7th molar. I'm going to do the same thing with 5 milliliters. Only this time I'm going to put my stock solution. I've added 5 milliliters. This is equal to my unknown concentration times the 250. Then I'm going to do 10. So it's 4.75 e to the minus 5 times 10 is equal to x times 250. We're also going to do this for 15. Then we're going to take these 4 solutions, put them into the UV, and we are going to get the absorbances. We're going to plot them, absorbance versus concentration. This is going to give us a straight line. We determine the slope. The slope is our molar absorptivity. Any questions so far, guys? Okay. Now, they're asking you to do a silly thing. And in retrospect, I found that it takes more time to do this than it takes to, it's worth it for the educational value you get out of it. What they tell you to do is they tell you to take the Gatorade straight, put it into the UV and get an absorbance and try and guess from there how much you have to dilute it. Okay. Basically, if you were doing this in a real experiment, you would have to do strict dilutions to see what your absorbance would have to be to get it on scale between 1 and 0. Don't worry about it. We've given you those values. You don't have to worry about that at all. There's going to be a line in your data table that says something to the effect of absorbance of the Gatorade straight or something like that. If there's a question in the results section, there is a number in the data table to put in there. Okay. But other than that, you don't have to do that for anything. We're giving you the volume and the volume and the absorbance you're going to need. Okay. Couple warnings again. If you have something like 2.33 e to the 7th, enter it in as 0.60233. The other thing, your graph must have a title. Your X and Y axes need to be identified. X is absorption, Y is concentration. If they have a unit, absorbance has no units, but concentration does. If it has a unit, you got to tell me what the unit is. In our case, it's going to be molarity. You're going to need a scale. If you do it in Excel, it's automatically done for you. If you do it by hand, you literally have to mark off the little boxes with numbers, and the numbers have to be equal distance apart from one another. The equation for the line has to be shown in the graph in some place. If you do it by hand, you must show me the work. If you do the slope by hand, do not use the data points. And again, remember, Y is the absorbance, X is the concentration. Okay, now we're set to do our sample. Okay. We dilute our sample down. We've put 30 milliliters of the concentrated solution into a 250 milliliter volumetric. When I did that, I got an absorbance of 0.421. I did my line graph, my graph of absorbance versus the concentrations. The slope of the line turned out to be 83,500. Ladies and gentlemen, the slope of the line has to be that big. It has to be either in the thousands or 10,000s. If it's not, then you've graphed your thing, your graph is wrong. I divide my absorbance by my slope. I get a concentration of 5.04 e to the minus 6 molar. But you have to remember, that's not the concentration of my Gatorade. That's the concentration of the diluted sample. And I know that my Gatorade originally was 30 milliliters. I don't know what the concentration of my Gatorade is, but my diluted sample was 250 milliliters, and I know its concentration. So I then have to go in and use M1V1 equal M2V2. X is the concentration of my Gatorade that gets multiplied by 30. The 5.04 e to the minus 6 is my concentration of my diluted sample. That gets multiplied by 250. I do this out and I get 4.21 e to the 5th molarity. That is the concentration of my dye in the Gatorade. Good to know, guys. This is with a smaller volume. So the number of the concentration of the Gatorade is going to be bigger than the concentration of the molarity of my diluted sample. That's really all I've got for you guys. Does anybody have any questions? Okay, second point. Second point is, guys, you have my phone number. Don't you all have my phone number? If you don't, copy this down. 727-202-7275. If you're running into problems, I had several people this week that basically threw their hands up and gave up. And if you have nothing else, give me a call. If I have time, I'll be happy to work with you. Now, don't call me at 3 o'clock on Sunday night. Chances are I'm going to be in bed. But please, if you're having trouble, give me a call. I may not answer you immediately, but I will try and get to you as soon as possible. Okay, that's it, guys. Angie?
Yes.
Okay. Guys, I'd like to speak to Angela alone. So that I just need to speak to her alone. Okay?
Yes, sir.
Thank you, Professor.
So you guys, good luck. It's really and truly, this is an easy lab to do. Not much to it, okay?
Thank you.
Take care.
Thanks.
Angie,
Yes, Professor.
okay. Are you understanding how to do calorimetry problems now?
Pretty much. Like I followed Dr. Musgrave's video, and I don't have a concrete understanding of it, but as long as I kind of follow that, I can solve through the
Okay,
problems.
let's go through it quickly, okay?
Okay.
I'm pulling up my video, yeah. Okay, when did Dr. Musgrave do this? It must have been a while ago.
I don't know.
He's usually like a month or so ahead of me. Okay, I'm working down towards it. Are you doing okay, Angie, in his class?
Oh, I'm not in his class. I was
Oh,
just watching the video.
Who do you have then?
Wait, say that again?
Who do you have?
I have you.
You got me for lecture?
Oh no. I didn't know you were talking about for lecture. For lecture, I have Thomas Selby.
Okay, I'm not familiar with which campus.
That I didn't check. Sorry
Okay.
about
Okay, I'm sorry. I'm trying to find. Okay, yeah. I know where I'm at now. Okay. Sorry, I'm trying to find this stuff out. Okay. I'm trying to find where my original, that looks good. Okay, Angie, do you do any cooking at all?
Yeah.
Have you ever worked with an iron skillet?
No.
Okay. That's too bad. All right. All right. Let me put it to you this way. Have you ever seen the grating on a gas grill?
I think so, yeah.
All right. That's made of iron. Turn the
Okay.
gas off. You turn the gas off immediately. Would you grab the grates?
No, because it's probably still hot.
Okay. Now, on the other hand, have you ever cooked something on aluminum foil in the oven?
Yeah.
Okay. Now,
It
yeah,
cools down pretty quick.
yeah, you can literally almost grab. I did it today for my lunch. I was heating fried chicken in aluminum foil, grabbed the foil out of the oven, put it on the burner, and literally speaking, like a second or three later, I was able to unfold it, right?
Yeah.
So when we're dealing with heat, the type of substance has something to do with the amount of heat it absorbs. Does this make sense to you?
Yeah.
Okay. So that is what I call S. Your professor may use a C, does he?
Mhm.
Angie?
Is it CS?
No. Does he use a C or does he use an S?
He uses a C, yeah.
That's fine. That's fine. But just understand that the C and the S, it's just different terminology.
Okay.
It stands for the same thing.
And I saw in the lab book it was C with a
Small
little
S.
S in the bottom.
Yeah, I don't actually, to be honest with you, off the top of my head, I'd have to research to see even what that little S means.
Yeah, okay.
But just understand that when I'm using S here, there's a reason I use S. Okay.
Okay.
So when I use the S there, that really means C to you. Okay.
Okay, yeah.
All right. Now, if you were cooking spaghetti for an entire fraternity, you'd need a pretty big pot of water, right?
Mm-hmm.
As opposed to cooking it for yourself, right?
Yeah.
So which one of the two do you think is going to take longer to heat?
The big pot.
Big one. So the mass of the water has something to do with the heat.
Yeah.
All right. Now, you heat the water to boiling, right?
Yeah.
All right. Or you have a bee sting and
A
you
bee
want
sting.
to you want to eliminate the poison that's in the bee sting. So you want to
Oh.
put it into hot water, right?
Mhm.
So same thing, you're using the same amount. The pot that you cooked your spaghetti in, or the pot you're going to heat up for you to put your wrist in to eliminate the bee sting, right? Are you going
Yeah.
to heat up the water as high a temperature?
No.
No, okay. So do you think it takes more heat to bring it up to boiling? Or do you think it takes more heat to bring it up to kind of like lukewarm tepid?
Probably to boiling it would take more.
So the change in temperature also has to do something with the heat that's absorbed. So we
Mhm.
have all these factors. The heat that's absorbed is equal to the mass of what you're heating times what the substance is, the C value, times the difference in the temperature from where you started to where you ended up.
Okay.
Does that make sense to you?
Yeah, that makes sense.
All right. Now, if you're throwing a metal cylinder into a water to get it to equilibrate, okay?
Mhm.
You want to find out how much heat that metal cylinder absorbs. Can you actually take a thermometer and jam it in there?
No.
So it's hard
You
to
can
do.
put
You
it
can't,
next to it.
you can't, yeah, you can put it next to it, but you don't know what the inner core temperature is.
Yeah, no.
So you have to do this indirectly. Does that make sense to you?
Yeah, like don't you wait for both the water and the metal to be the same.
Yes, you do.
Equilibrium.
Equilibrium. Okay. So what you can measure the temperature change in the water, you can't really with the metal.
Mm-hmm.
All right. So there is also, do you remember at the first of this chapter where we were talking about systems and surroundings? We can't ever lose the energy. The energy, total energy of the universe is going to be equal to the system plus the surroundings. Does that make sense to you?
Yeah, because energy is conserved.
Absolutely. So if we have that the total energy of the universe is equal to the surroundings plus the system, when the system loses energy, what happens to the surroundings?
Probably gains energy.
Gains energy. When the system gains energy, what happens to the surroundings?
They lose energy.
So it's the same amount of energy,
It just
but
transfers.
opposite signs.
Mm-hmm.
Does that
Oh
make
yeah,
sense to you?
yeah, yeah.
So
I see
what
where
we are
you're
going
going.
to, I'm sorry, go ahead.
I see where you're going with this.
So basically, and okay, I'm going to try and find out where I have that. I'm doing this haphazardly. So, okay, here it is. So we have to agree that the system, and you have to define what the system is. In the terms of our metal, our system is just the metal. Everything else is the surroundings. So that when if I'm taking that hot metal, I'm putting it into water, that metal is losing heat.
Mm-hmm.
So it has a negative sign. The surroundings, by the surroundings, I'm talking about the water, that is gaining heat.
Mm-hmm.
So if I'm doing a problem, I'm just going to do one problem, and then I'm going to let you go because I want to eat myself, okay?
Okay.
What is the specific heat of a metal bar that weighs 54.234 grams? It's put into boiling water. If the metal's put into boiling water, what's the temperature of the bar initially? It's in boiling water.
Probably 100.
100
If it-
degrees, okay? Then I transferred it to a calorimeter. The calorimeter had 225 grams of water. The water started at 25.2 degrees Celsius. The equilibrium temperature, in other words, the metal went down from 100 degrees, the water increased. The metal
Mhm.
went down from 100 to 27.1 Celsius. So that 21.1 Celsius is not only the final temperature of the water, it's also the final temperature of the metal.
Mm-hmm.
So I can use this expression. I can say, remember, Q is equal to MC delta T, right? So
Yeah.
I could take my surroundings of the water. I could take my mass of the water times my specific heat of water, which is 4.184, times 27.1 minus 25.2.
Mm-hmm.
And that is equal to negative. Then I'm going to take the mass of my metal, 54.234 grams. And I'm going to multiply that by the specific heat, which I don't know, times 27.1 minus 100.
Mm-hmm.
And I'm going to do that. I have to do that in a big, long problem. Or I don't. Okay. I can solve for the Q of water. I have the mass of water times the specific heat times the temperature change. I get 1788.66 joules. When you're doing these problems, Andrew,
Mm-hmm.
when you're doing these problems, do you see this number over here? 27.1 minus 25.2. That gives you 1.9 degrees centigrade, right?
Yeah.
99% of the time you are dealing with these problems, the significant figures are going to be dictated by your temperature change.
Okay. Okay.
So I did this rough. I did the rough calculation. I came out with 1788.66 joules. But I also know that my Q of my water, which are the surroundings, is equal to negative the Q of the metal. So the Q of my metal is going to be negative 1788.66, which in turn is going to be equal to the mass of my metal times the specific heat, which I'm trying to solve for, times my T final minus T initial of my metal. I got this. I do the math out. I get 0.45 joules per gram centigrade. Notice I haven't done any significant figure changes until the very end.
Mm-hmm.
My first temperature change had 2 sig figs. That dictates that my final answer is going to have 2 sig figs. I don't know whether it helped Angie or not, but it was clear that when you were doing the report, you didn't understand what was going on.
Yeah.
Okay, that's all.
All right. Thank you.
You have a good night, all right?
You too.